Hello, Ria. I'm going to explain this problem to you. Basically, it's pretty simple. All you have to do is just understand the difference between an enantiomer, diastereomer, and a constitutional isomer. All right, so let's see. Let's go to the first one. But first off, you got to understand that between a constitutional isomer, diastereomer, and an enantiomer, you have to understand that um, all three of those are isomers. Isomers basically are organic compounds that have the same uh, formula, but they have different structure, which means that they're shaped different. Now, of course, if you have a isomer, which means you have you have two different organic compounds with the same formula, but they have a different structure. That now it can be two types. One type can be stereospecific, and one can be non-stereospecific. The one that is stereospecific is it differs in three-dimensional space. So, what do I mean? Let's talk about enantiomer first. So, like when you say enantiomer, diastereomer, or when you say constitutional isomer, you're talking about a very specific type of isomer. So, enantiomer, remember, like I said before, enantiomer can be stereospecific or non-stereospecific. Enantiomer is stereospecific, which means it differs in three-dimensional space. Only thing specific about enantiomer is it has four different connections: A, B, C, and E here. I should have put a D right there, but anyway, you can see the four different colors. That's what that is. All right, so we got a constitutional isomer. It's pretty simple. It has the same formula. Like for instance, we got these two different compounds. We got compound number A and compound B. I mean letter B. So between the two, basically, has the same formula as you can see. Two carbons. One of the carbons is red and one of them is purple. So like you see that like to the left, you got a compound called dimethyl ether, but to the right you got an ethanol. I mean, we get drunk off of ethanol all the time. So basically, you got two different formulas, but at the same time, you have different structures. And the different structures give you two different names. Like I said, the one figure A is dimethyl ether, because ether because that's the functional group, and dimethyl because it's got two methyl groups, 1 and 2, the purple and the red carbon. So again, if you go to the right to the figure B, you got a situation where you have carbon number 1 and carbon number 2. And of course, carbon number 1 is the purple one, carbon number 2 is the red one. Again, like I'm saying, I just want to really emphasize here, the only difference is the connectivity. Oh, also, the very important thing here, differentiate constitutional isomer from an enantiomer. Constitutional isomer is not a stereospecific, which means that it has no three-dimensional relatedness to it. Let's go back to this for a second. So notice that you got let's call this figure C and figure D. Figure C and D are enantiomers of each other, and they're like stereospecific twins of each other. They're twins in the way they're twins, but they're different in the way that they're like left and right hands of each other. Okay, so let's go to the last one. The answer to the question is that the actual compound is the diastereomer. Why is it diastereomer? Okay, diastereomers are stereospecific. And notice anytime you have something that's stereospecific, they try to show these, like in figure number 2, you can see here, they're trying to show like the spatial reasoning of the compound. Okay, let's get to explaining the compound a little better. Okay, so specifically the spatial reasoning between the two is that it's in the cis transformation. If you look at figure 3 versus figure 4, as you can see, I'm trying to relate all these compounds and drawing them many times. So all 1, 2, 3, and 4 are the same compound, but I'm just trying to differentiate them by like showing them from different perspectives. Okay, if you look at number 3 and 4 specifically, I'm trying to show you the cis trans relationship between all the carbons. I even specifically go start at compound figure number 1, and you can look at the compound and you can see that basically I'm lettering the compound and I'm trying to show you what the carbons are in relation to each other in three-dimensional space. And specifically, if you're looking at this compound, you can see it's a diastereomer because carbon number A and B are the carbons of the double bond, and carbon C and D is what make the cis and trans in the two different situations. So so basically, this is the answer, that this compound is a diastereomer, but also just an extra clue. All double bonds are diastereomers because they're always going to be cis and trans. But anyway, basically, check my channel out if this was helpful, please, and I can, help you on other subjects, and also I can explain this concept in more depth or more questions. Thanks.